In this video, we're going to talk about polynomial function. A polynomial function is a function that has many terms in it. Now, what do we quantify as many? It could be as little as 2 terms, to as many as 10, 12 terms. It can go on, for however many terms you like. Now, what makes it a polynomial, though, is that we have to make sure that the exponents on the x must be whole numbers. So in other words, if you have terms in your function that, let's say, have a fraction in the power of the x or a negative in the power of the x, that would not be a polynomial function. Okay, so the main thing to remember is that the powers, they have to be positive whole numbers. Okay, so we cannot have powers of x that are fractions or negative. So down here we have some examples of some polynomial function. And when we discuss polynomial function, it is often good to know what the degree of the polynomial is. And what we call the degree is the highest power. So for instance, right here, we have a polynomial function. This function has 4 terms in it. If I ask you what's the degree of this function, it's going to be degree 5. And that's because if you look at all your terms, the term with the highest power on the x is 5. Here is another function, 3x squared plus 7x minus 1. This is again a polynomial. And this is a polynomial of degree 2 because the highest power on the x is 2. This next one, the function f of x equals 5x minus 1, will have degree 1 because the highest power on the x is 1. 5x is the same thing as 5x to the power of 1, and that's the highest power in this case. Down here, we have an example of a function that is not a polynomial. And the reason why this function is not a polynomial is because of 2 terms that we have in this function. First, the function 4 square root of x. So the thing about the square root is that we can write the square root as a power. And the square root is the same thing as power 1/2. So when I say 4 square root of x, we can write that as 4x to the power of 1/2. So this term here will make this not a polynomial because the x has a power that is a fraction. Going back to what we talked about a minute ago, we said that we cannot have powers of x that are fractions or negative. So the term 4 square root of x has a fraction in the power of the x, so that would make it not a polynomial. Another reason why this is not a polynomial is the term 3 over x. The term 3 over x, we can rewrite that as 3x to the power of negative 1, because 3 over x, the x that's in the denominator, we can think of that as x to the power of 1. If I take the denominator and move it to the numerator, what happens when you move the x to the numerator? It's going to change the sign in the power. So if you have x to the power of 1 in the denominator, when you move it to the numerator, it becomes x power negative 1. So if you write it as x power negative 1, we now have a negative in the exponent, and that is something else that we can't have with polynomials. So this is not a polynomial because of the powers on the x. Now, when it comes to the domain of polynomial functions, the domain of a polynomial function is always going to be all real numbers, or in interval notation, it's going to be from negative infinity to positive infinity. And that's because if we look here, these are all examples of polynomials. You notice that polynomials don't have any square roots of fractions in them. Because they don't have any square roots of fractions in them, they are going to be all real numbers for the domain. When it comes to the graph of polynomial functions, graph of polynomial functions are smooth and continuous. Okay, so this first graph here is an example of a graph that is smooth and continuous. So it's a continuous curve, smooth curve. So this right here, this first example, is a graph of a polynomial. These other cases here that we have, those three other graphs that I have, those are not polynomials. And the reason they're not a polynomial is because, well, if we look at the first case, this one is not a smooth graph because we have a sharp point in the graph. The second one is not continuous because we have a break in the graph, okay, right here where the y-axis is. And then the last graph is also not continuous because you see we have a hole right there and also another break in the graph right here. Okay, so these are not continuous graph. Continuous means like it's one nice continuous line. Okay, we don't have any breaks in the line. And then also the curves, it's nice smooth curves as opposed to being sharp corners in the graph. So that's what I mean by smooth and continuous. The next thing we're going to look at with these polynomials is something called the end behavior. So the end behavior tells us what the graph does on the ends. Okay, so what I mean by what the graph does on the ends is we're interested to know the direction that the graph is going. Okay, so we want to know, is it going up or is it going down? So down here I have some examples. Okay, so you notice that the first graph here is a nice continuous smooth curve. So these are all graphs of polynomial functions. The first graph, you notice that on the left side, the graph is going up, as well as on the right side of it, the graph is going up. So both the left side and the right side, your graph is going up. In the second case, both on the left side and the right side, the graph is going down. In the third case, on the left side, the graph is going down, and on the right side is going up. And then on the last case, the left side of the graph is going up, and the right side of the graph is going down. Okay, so we're interested in knowing what the end behavior is. So the end behavior is the direction that the graph is going on the left side and on the right side. So to determine the end behavior, we are going to look at the leading term. What the leading term is basically the term that has the highest power. Term with highest power. That is what we call the leading term. What we're going to do with that term is we're going to look at two things. We have to look at the power, and we're going to determine if the power is even or if the power is odd. And then we're going to look at the number that's in front of the x. We want to see if the number in front is either a positive number or a negative number. That's what is going to help us figure out the end behavior. So for instance here, like if your power is even and the number in front is positive, then that tells me that on the left and on the right, your graph is going to be going up. Okay, and here are the other cases when the power is even and the number is negative. When the power is odd, the number is positive. The power is odd, the number is negative. So let's look at some examples here and try to figure out the end behavior. Here is my function f of x equals negative 4x to the power of 5 plus 6x to the 4th plus 2x. We only care about the term that has the highest power. In this case, that's the term negative 4x to the power of 5. So what we're going to do is we're going to look at n. N is the power, okay? So n is equal to 5 in this case, which is an odd number. And then we're going to look at an. an is the number in front of the x. In this case, it's -4. So it's a negative number. Okay, so we'll look at two things. We have to see what the n is. N is the power, and an is the number in front. So in this case, we have it to where the power is odd and the number in front is negative. So when the power is odd and the number is negative, here is my n behavior. On the left, my graph is going to go up, and on the right, my graph is going to go down. So I'm going to say on the left, it goes up, and on the right, it goes down. Here's another example. We're going to look at the term with the highest power. So that's the 0.3x to the power of 4. My power in this case is 4, which is an even number. And then my an is 0.3, which is a positive number. So if I have an even power with a positive number in front of it, then my n behavior would be up on the left and up on the right. So on the left, my graph is going to go up, and on the right, it's also going to go up. The next one here is also a polynomial. However, in this case here, what we have, it's a polynomial in factored form, okay? When it's written like this with the parentheses, it's called factored form. So when we have something in factored form, okay, so when in factored form, we are going to add each power to find n. Okay, so we're going to add, I'm going to rewrite this. We're going to add, I'm going to rewrite this as add power of each factor add power of each factor to find n. And then we're going to multiply the signs of the coefficients for an. Okay, let me explain to you what I mean by this. So first of all, let's look at all the factors. So I have 1/4 x. So this x here is the same thing as x power 1. And then I have 2x minus 3 power 3, and then x plus 4 power 2. We're going to add the powers of each factor. So here, to find n, we're going to take 1 plus 3 plus 2. That's going to give me 6, which is an even number. And then now for an, we are going to look at the signs of the coefficients. So the coefficients means the number that are in front. So in front of this x, I have 1/4. That's a positive number. In front of the 2, or yes, in front of this x, I have 2, which is again a positive number. And in front of this x, I have a 1. If it's just x, remember, we can think of that as 1x. That's again a positive number. So if I have a positive number multiplied by a positive number multiplied by another positive number, that's going to give me a positive number. So my an is going to be positive. So if I have a situation where the power is even and the number is positive, so power is even and the number is positive, that my n behavior would be up on the left and up on the right again. So that's what I'm going to write here. So on the left, my graph will go up, and on the right, my graph will go up. In this last example, again, this is in factored form. So to find n, I'm going to add the power of each factor. So this -6/7 in front did not have an x in it, so I'm not going to include that. This first factor had power 4, the next factor had power 2, and the last factor has power 1. 4 plus 2 plus 1 is 7, which is an odd number. Now to figure out an, we're going to look at the numbers in front. So the number in front I have -6/7, which is a negative number. In front of this x, I have a 1, which is a positive number. In front of this x, again, I have a 1, which is a positive number. And in front of that x, I have a 3, which is a positive number. When I multiply a negative times a positive times a positive times a positive, I'm going to end up with something that's negative. So an odd power with a negative number in front of it, the end behavior will be up on the left and down on the right. So on the left, my graph will go up, and on the right, my graph will go down. That's how we find the end behavior. In the next part of this section, we're going to talk about the zeros of a polynomial. The zeros of a polynomial refers to what we call the x-intercept. The x-intercept is a point on the graph where it's going to cross the x-axis. The x-axis is the horizontal axis. So let's say I have a graph that looks like this. This graph is going to have 2 zeros. One of the zeros is going to be at this point right here, and another one of the zeros is going to be at this point right here. Okay? So there are 2 ways that your graph can cross the x-axis. So it can actually cross it, or in other words, it goes through the x-axis, or it can just touch the x-axis and then turn around. Okay? So when it goes through the x-axis, like we see right here, we call this a cross point. And if it just touches the x-axis, we're going to call that a touch point. So when we're finding the zeros of a polynomial, they can sometimes be cross points, they can sometimes be touch points, and we're going to know which one it is based on something called the multiplicity. The multiplicity has to do with the power of the factors. Okay, so the multiplicity has to do with the power of the factors. So in order for us to find the zeros, what we're going to need to do is we're going to have to factor our function. Let's look at some examples where we're going to need to do that. The first function we have is the function f of x equals 4x cubed minus 4x squared minus 25x plus 25. This function has 4 terms, and we're interested in finding the zeros. So when we have a function with 4 terms, we're going to factor by using something called factor by grouping. So what we're going to do here is we're going to group our function in groups of 2. Okay, so my function is 4x cubed minus 4x squared minus 25x plus 25. What I'm going to do is I'm going to group the first 2 terms together and the last 2 terms together. Now, for the first 2 terms, I'm going to factor out what they have in common. So out of these 2 terms, what they have in common is a 4x squared. If I factor out a 4x squared, I'm going to be left with x minus 1. And then out of the last 2 terms, they both have a 25 in common, but because this first 25 has a negative with it, I'm going to factor a negative 25 out. When I factor out a negative 25, I'm going to be left with x minus 1. Now you notice that both of these had a factor of x minus 1 in common. So what I'm going to do is I'm going to factor out that x minus 1. So I'm going to pull this x minus 1 out in front. When I pull that 1 in front, what I'm left with is going to be the 4x squared minus 25. Now 4x squared minus 25 is something that I can factor further. And that factors to 2x plus 5, 2x minus 5. What I've done here is I've used something called difference of squares. 4x squared minus 25, so the 4 and the 25, these are both square terms, and you're subtracting them. So difference of squares is a special type of factoring, which says if you have something squared, let's say a squared, and you're subtracting something else squared, let's say b squared, that would factor to a plus b, a minus b. We call that difference of squares. All right, now we have completely factored our polynomial. The original function was this with 4 terms. We've factored it. What I'm going to do now to find the zeros, I'm going to set this equal to 0. Once I set this equal to 0, I'm going to set each factor equal to 0 and get x by itself. Okay? So if I set x minus 1 is equal to 0, that's going to give me x is equal to 1. If I set 2x plus 5 is equal to 0, I'm going to get x by itself by subtracting 5 and then dividing by 2. That's going to give me x equals negative 5/2. And then if I set 2x minus 5 is equal to 0, I'm going to get x by itself. So the first I'm going to add 5 to both sides and then divide by 2. So that's going to give me x equals positive 5/2. So 1, negative 5/2, and positive 5/2 are the zeros of my function. This is what I call the zeros. But now we need to know whether these zeros are going to be cross point or touch point, like we discussed on the previous page. So to determine if it's going to be a cross point or a touch point, we're going to look at the multiplicity, like I mentioned earlier. And the multiplicity is the power of the factor. If the multiplicity is an odd number, then your 0 is going to be a cross point. If the multiplicity is an even number, then your 0 is going to be a touch point. Again, the multiplicity is the power of the factors. So here, my factors are x minus 1, 2x plus 5, 2x minus 1. And you notice that we have one of each of those factors. In other words, the power on each one of them is 1. Okay, so this x minus 1 is just power 1. The 2x plus 5 is power 1. The 2x minus 5 is also power 1. So the power is 1 on each one, which is an odd number. So because it's an odd number, that means it's odd multiplicity. So they all have odd multiplicity, which means they're all going to be cross points in this case. So all these zeros for this first function are all going to be cross points. Let's look at the next one. So the next function is x cubed plus 10x squared plus 25x. Here we only have 3 terms. So with 3 terms, we cannot do by grouping. So here we're just going to have to factor our function. So factoring means here, what I'm going to do first is I'm going to look and see if my function has something in common. If they all have something in common. You notice that something that they all have in common is an x. So I'm going to pull out an x. So if I factor out an x, I'm going to be left with x squared plus 10x plus 25. Now I'm going to see if I can factor the x squared plus 10x plus 25 even further, which I'm able to do. So to factor this, I have to find 2 numbers that will multiply to give me 25 and add to give me 10. those two numbers would be 5 and 5. So x squared plus 10x plus 25 would factor to x plus 5, which I can also write as x plus 5 squared. So here's my factored form. This is what my function is. This is a factored form of it. So when it's in factored form now, I'm going to set it equal to 0. And I'm going to set each factor to equal 0 and find x. So the first one, if I set x equal to 0, is just going to give me x equals 0. And then the second one, if I set x plus 5 is equal to 0, when I get x by itself, it's going to give me x equals negative 5. So my zeros here are 0 and negative 5. Again, those represent the points on the graph where it's either going to cross the x-axis or touch the x-axis, which we now need to figure out whether it's going to cross or touch. So to determine that, we're going to look at the power of each factor. So the first one was x. This is x power 1. So 1 is an odd number, or we can also think of that as what we call the multiplicity. So 1 is an odd multiplicity. Whenever the multiplicity is odd, that tells me that my 0 is going to be a cross point. The second factor was x plus 5 squared, so the power is 2. The multiplicity is an even number. Whenever it's an even number, that tells me that on my graph, the 0 is going to be a touch point. And again, let me remind you what I mean by being a cross point or a touch point. A cross point means the graph goes through the x-axis, so it's crossing the x-axis, whereas a touch point is a situation where the graph is going to touch the x-axis and then turn right back around. So that's what we have here. In this example we just did, we have one of each. In the next example, I have the function f of x equals x to the power of 4 minus 2x squared. So here I only have two terms. So again, I'm going to solve this by simply factoring. So what I'm going to do is I'm going to see what they have in common. The two terms, for these two terms, what they have in common is an x squared. So after I factor out an x squared, so I take an x squared, I'm going to be left with x squared minus 2. What I'm going to do next is, so this is the factored form of it. I am now going to set each one equal to 0. So if I set x squared is equal to 0, that's just going to give me x is equal to 0. And for the next one, if I set x squared minus 2 is equal to 0, that's going to give me x squared is equal to 2. And to get x by itself, I'm going to have to take the square root of 2. Whenever I take the square root of 2, remember you would have to add plus or minus. Okay, so we actually get 2 zeros from this. I have x equals negative square root of 2. And x equals positive square root of 2. So those are my other zeros. Now, to determine if the zeros are crossing or touching, the first one, it was x squared, so this was power 2. So the multiplicity is an even number. When it's an even number, that tells me that my graph is going to be a touch point. Now this factor here was x squared minus 2. Now I do realize that we have x squared, but this we have to look at the whole factor. The factor itself is x squared minus 2, and we only had one of those. Okay, so in other words, like if you look at what I have in parentheses, okay, everything in parentheses, we only have one of them. So that means it's going to be power 1 out here. So that's what the multiplicity is going to be for this term, x squared minus 2. It has multiplicity 1. So 1 is an odd number. So that means it's going to be touch points for both of these zeros here. I'm sorry, they're going to be cross points for both of these zeros because 1 is an odd number, so it's an odd multiplicity. Okay, so this is going to be a cross point, as well as this one is going to be a cross point. For the final example, we have the function x squared, x minus 2 cubed, x plus 4 to the power of 7. The nice thing about this one is that it's already in factored form. So what we have to do, if it's already in factored form, we simply just have to let each factor equal to 0 and then solve for x. So the first one, if I set x squared equal to 0, that's just going to give me x is equal to 0. There is my first 0. The second one, if I set x minus 2 is equal to 0, that's going to give me x is equal to 2. Here's my second 0. And then the last one, if I said x plus 4 is equal to 0, that's going to give me x equals negative 4. There is my third 0. Now, as far as whether these are cross points or touch points, we're going to look at the power of each factor. That's what we call the multiplicity. So the first one, x squared, that's 2. The power is 2, so the multiplicity is an even number. When the multiplicity is an even number, that tells me that it's going to be a touch point. The next one, the power was 3 on the factor, so that means it's an odd multiplicity, it's an odd number. So that means at 2, it's going to cross the x-axis, so it's going to be a cross point. For the last one, again, it was power 7, so the multiplicity is 7, which is an odd number. So at the point negative 4, my graph is going to cross the x-axis as well at that point. So that's how we find the zeros. We first factor our function and we set it equal to 0. And then we're gonna factor it. We're gonna set each factor equal to 0 and solve for x. And then to determine if it's crossing or touching, we look at the power of each factor. For the last part of this section, we're going to look at how to graph a polynomial. Now, before we can graph a polynomial, there are certain things that we're going to have to figure out first. And that list of things is listed right here in your notes. So first, we're going to have to figure out the end behavior, which we've already discussed how to do. Then we also have to figure out the y-intercept. We're going to then figure out the x-intercept. We're going to talk about the number of turning points. And then we're going to finally go into sketch the graph. So the end behavior is something we've already discussed at the beginning of the section. To find the y-intercept, we're going to plug 0 for x. To find the x-intercept, we are going to find the zeros. We just discussed how to find the zeros. And if you remember, I mentioned that the zeros is the same thing as the x-intercepts. So we're going to find those and then figure out if they're cross points or touch points. And then we're going to have to figure out the number of turning points. So to find the number of turning points, it's going to be the highest degree minus 1. What that means is we're going to take the power and we're going to subtract 1 from it. Okay, so n minus 1 is another way to think about it. That's how we're going to get the number of turning points. And then as far as sketching it goes, we're going to use our calculator for that part. All right, let's do the first example. My function is negative x cubed plus 4x. Let's figure out the end behavior first. So the end behavior for that one, we're going to look at the term that has the highest power, which is a negative x cubed in this case. So my power n is 3, which is an odd number. And then the number an is the number that's in front of it. It's the coefficient is what we call it. And that number is a negative 1, which is a negative number. So going back to what we discussed at the beginning of this section, if you have an odd power and then the number is a negative number, the end behavior will be that on the left, your graph is going to go up, and on the right, your graph is going to go down. This is the end behavior. Next, we're going to talk about the y-intercept. So to find the y-intercept, it's just a matter of plugging in 0 for x. So to find the y value, I'm going to replace x with 0. So negative 0 cubed plus 4 times 0, that's going to equal to 0. So my y-intercept will be the point 0, 0. For the x-intercept, we are going to set our function equal to 0. And then we're going to factor, because finding the x-intercepts is like finding the zeros. So we find the zeros by factoring. So we're going to see what do our two terms have in common. Both terms have an x in common here. And because the first term is negative, I'm going to also include the negative with a factor. So I'm going to pull out a negative x. When I pull out a negative x, I'm going to be left with x squared minus 4 equals 0. And x squared minus 4 is what we call a difference of squares again, because 4 is the same thing as 2 squared. So I can factor that further as x plus 2, x minus 2. And we're going to set that equal to 0. So this is my factored form. What I'm going to do now is I'm going to set each factor equal to 0 individually. So the first one, if I set x equal to 0, that's just going to give me x equals 0. The next one, if I set x plus 2 equal to 0, that's going to give me x equals negative 2. And the last one, if I set x minus 2 is equal to 0, that's going to give me x equals positive 2. Now, we also need to figure out if these are going to be cross points or touch points. Looking at the factored form, we have one of each. So they each have power 1, which is an odd number. So the multiplicity is odd. Because the multiplicity is odd, they are all going to be cross points. Okay, next we need to find the number of turning points. So to find the turning points, we're just going to do n minus 1. N is whatever the power was. The power was 3. So 3 minus 1 equals 2 in this case. So our graph is going to have 2 turning points. Turning point just means like how many times the graph turns. I'm going to show you that when we graph it. Okay, so that's going to be the last step, is the graphing part of it. We're going to use our calculator to help us graph. So on the calculator, we're going to go to the y equals, and then we're going to type in our function. My function here is negative x cubed, x power 3 plus 4x. I'm going to hit graph, and here is my graph. So it is good before we draw this to make sure that everything looks correct. For instance, we said that on the left side, my graph has to go up, and on the right side, my graph has to go down. We do see that it does that here. On the left side, it's going up. On the right side, it's going down. It's crossing the y-intercept at 0, 0. As far as the x-intercepts goes, we have 3 of them right here at 0, and then right here at positive 2. So negative 2, 0, and positive 2, just like how we had found. And then we decided that they were all cross points. You see that on the graph, they all cross the x-axis there. And then we also looked at the turning points. We said we have 2 turning points. You see here that there are 2 turning points. Okay, so a turning point is where the graph turns. There is this point right here that's a turning point, and then this point right here that's another turning point. Okay, so I'm just going to sketch this on my paper, and I will have my graph. The graph looks something like that. Finally, we have one more example that we're going to do where we're going to be graphing this function. But before we can graph this function, we're going to first find the end behavior. This is a function that is in factored form. So as discussed previously in this section, when it's in factored form, to find the power n, we are going to add the powers of each factor. So in this case, 1 plus 1 plus 2. That's going to give me 4, which is an even number. And then to figure out an, we're going to look at the coefficients. The coefficients are the numbers that are in front of my x. We are going to see whether they are positive or negative numbers. So for the first one, I had 0.5x. 0.5 is a positive number in front. Next one, I have x minus 1. So x is the same thing as 1x, so that the number 1 is a positive number. And then the last one is x plus 3. So again, that's a 1x plus 3. So 1 is a positive number. When we multiply numbers that are all positive, that's going to give me a positive number. Okay, so when my power is even and the number is positive, the end behavior is that on the left side, my graph will go up, and on the right side, my graph will also go up. Next, I'm going to find the y-intercept. So the y-intercept is where I plug in 0 for x. So 0.5 times 0 times 0 minus 1 times 0 plus 3 squared. You can try to do this on your calculator if you would like. This is going to come out to just equal to 0 in this case. And so that will tell me that my y-intercept is going to be the point 0, 0. Next, we're going to figure out the x-intercepts. So the x-intercepts are the zeros. So this is where I'm going to take my function and I'm going to set it equal to 0. This is already in factored form, so I do not have to factor this. I simply just have to set each factor equal to 0 and solve for x. So if I set 0.5x is equal to 0, I get x by itself. That's going to give me x is equal to 0. Next, if I set x minus 1 equal to 0, I get x by itself. That's going to give me x is equal to 1. And the last one, if I set x plus 3 equal to 0 and I get x by itself, that's going to give me x equals negative 3. So I have 3 zeros, or I have 3 x-intercepts at 0, 1, and negative 3. Now I have to figure out if those are going to be cross points or touch points. The cross points and touch points come again from the power of each factor. So 0.5x, that's the same thing as x power 1. So this power is 1, which is an odd number. So the multiplicity is odd. When the multiplicity is odd, that tells me that it's a cross point. Same thing for x minus 1. It was power 1. I only had one of them. So that's an odd multiplicity. So at 1, I'm going to have a cross point again. And then the last factor was x plus 3 squared. So the power is 2 on that one. So it's an even multiplicity. So that means at negative 3, my graph is going to touch the x-axis. It's going to be what we call a touch point. So I have found my x-intercepts right here. Next, I'm going to figure out the number of turning points. To get the number of turning points like we talked about earlier, it's the degree minus 1, so n minus 1. In this case, n was 4. We had calculated this earlier when we were figuring out the n behavior. So 4 minus 1 is going to be equal to 3. My graph has 3 turning points. So now I'm going to actually graph it. We will do that, like I said, on the calculator. We're going to go to y equals, and I'm going to enter my function 0.5x parenthesis x minus 1 close parenthesis, another parenthesis, x plus 3 close parenthesis squared, and we hit graph. Let's confirm. So on the left and on the right, my graph has to be going up. We see that here on the graph. It's going to cross the y-axis at 0, 0, which we see right here at 0, 0 is crossing the y-axis. There are 3 places where it crosses or touches the x-axis. So right here, this is at negative 3, and this is a touch point. You see how it touches the x-axis and turns around. That's a touch point, which is what we had figured out. And then at 0 and at 1, it's crossing the x-axis because it goes through the x-axis at those 2 other points. So that looks good. And then finally, for our turning points, we had figured out we had to have 3 turning points. On my graph here, I have 1, 2, and 3 turning points. So that looks good. Let's go ahead and draw a picture, and we will be done. So at -3. Okay, so my graph does this. Goes up, cross, turns around, and then goes back up. And this is just a sketch of my graph. This is the graph of the polynomial 0.5x times x minus 1 times x plus 3 squared. And this is how we graph polynomials.